Everyone. Thanks for joining me again. This will be a very short video. It's just tidying up the last part of these section of notes based on, and we're going to have a look at the strength of the magnetic field around a current carrying wire. Okay, so you have a wire. What's the quantity of the magnetic field in Teslas? So what's and the magnetic field strength is a capital B, and the unit is a Tesla. So the question is what does um, magnetic field strength for a current carrying wire depend on? What does it depend on? Question mark. Okie dokie. So if we think about this, well, obviously the first thing it would depend on is the amount of current flowing through. So it's directly proportional to the amount of current. And if you think about how, if you move further away from that wire, obviously your magnetic field strength is going to decrease. So it's radially because we remember the magnetic field is circular. Okay. And so therefore it's inversely proportional to the radius you are away from it. Okay. And so we know, so therefore we can combine that and say that B is therefore proportional to I, inversely proportional to R. Okay, so there must be some sort of constant which we can find graphically. If we find this constant and we experimentally we change the amount of current and we measure. We change the amount of current and measure the magnetic field, and change the amount of radius and measure the magnetic field strength. Then there should be some constant tying them together to make this an equality. Okay, so it turns out that constant K is this thing called mu naught over 2 pi. Okay, so this is the permeability of free space. Okay, and this is in your formula data and formula booklets. Okay, so we end up getting that the magnetic field is this permittivity times by the current divided by 2 pi r. Okay, or the circumference. Anywho, so that's what it is. Okay, so and that permeability of free space or magnetic constant is given here, 1.26 times 10 to the minus 6. So let's do a quick example, and this is only to be used for a single current carrying wire. This formula can't be used for a solenoid because that's a coiled wire. Okay, that's different. So this can only be used for a straight wire and to find the magnetic field around it. Okay. All right. So let's do an example. Calculate the magnetic field strength in Teslas at a distance of 10 centimeters from a long wire. So the first thing I see the distance d, or the radius, is 0.1 meters. Okay, these are SI units, and that the current is 10 amps. Okay, so I'm going to indicate this for the examiner straight away. The next thing is I'll have a look. Okay, it's just a current carrying wire, so I know that the formula for this from my book is mu naught times I over 2 pi r. Okay, so this is for just a single current carrying wire. So the field strength is going to be 1.26 times 10 to the minus 6 times by the current was 10 amps divided by 2 times pi times the radius was 0.1 meters. Okay, and I'm just going to grab my calculator. So it turns out to be 1.26 x minus 6 times by 10 divided by 2 times pi divided by 1. And the answer is 2.005. 2.0053 times 10 to the minus 5 Teslas. This is really messy, sorry. So it's 2.0053. So to three significant figures, that would be 2.00 times 10 to the minus 5. No, sorry, I'm wrong. It would be 2.01. So 2.01 times 10 to the minus 5 Teslas, okay? That's the answer. We want to indicate that to the examiner. Okay, so a current of 2.45 amps is flowing vertically upwards. All right, so this is conventional current, so it's 2.45 amps flowing upwards. So I know that, I mean, this is just going through my mind. I know that if I use my right-hand thumb rule, this might not even be related to the question, but I know that, you know, I'm going to have a field going this way. So my magnetic field is going that way, okay? And if I draw that via dots and crosses, this is coming up out of the page and this is going into the page. I can draw, this is the same thing as that, okay? This is the same thing as drawing that. So this would be a dot and the point where it enters would be a cross. Okay. Alrighty. Calculate the magnitude of the magnetic field created by this current at a point located this many centimeters from the conductor. Okay, so this is very similar to the first one. You guys can try this one yourselves. Thanks, guys. So today we had a quick look at if you have a single current carrying wire, not a coiled wire, because I'm sure there is a formula for the magnetic field strength around a coiled wire, but we're not talking about solenoids. Okay, we're not talking about solenoids. We're talking about a single current carrying wire. Okay, what is the magnetic field strength around a single current carrying wire? And we had a look at that, and it turns out that this is equal to the permeability of free space. So it depends on the substance that you're in, divided by times by the current divided by 2 pi r. Okay. Thanks.